Hello, this is the final lecture for the lecture series of Renaissance of American Physics and Astronomy at the ISU chapter. Today's subject will be very high energy astroparticle physics. So to give you a little bit of background of my experience in this field, for which I was a grad student for about 2 years. Before I even wanted to come to America to start my physics career, I had the mainstream attitude of knowing the most epic scientists ever, getting Nobel Prize, joining NASA, going to the best university, yada yada yada, and hoping that one day that my words would be heard by the people. And by the time I made it to grad school, I embarked on quite a lucky opportunity, I would say. I uh, I was applying to schools pretty close to my nephew's, and I noticed one of the fields I wanted to study at Iowa State, high energy astrophysics. Not only that, but I could finally actually study theoretical particle physics for a change. And I embarked across an international collaboration that's quite advanced at what it seems to be an underrated school that's not too difficult to get into. So it was more or less I felt like I won the lottery, to be honest, and I I completely had a different perspective of my priorities, even though I didn't really get what I want, but it seems like I got a much better deal, to be honest. I wanted to come here also to avoid the drama in academia physics as much as possible, even though that still somehow backfired. I met a lot of smart physicists before I came here and after I came here through the collaboration. Um, and I feel like I really fulfilled my goal of becoming a scientist. And I no longer fear for the sake of Egypt as much as I did. So, getting on to the subject, this was a snapshot of the previous lecture series showing you a bit of highlights of high energy astroparticle physics. I'm specifically going for very high energy, which you can see on the bottom left. You can see electromagnetic spectrum. If you go higher and higher in energy, you oscillate the vacuum at more rapid pace, and you get shorter and shorter packets of light and get shorter and shorter gamma rays. That's what we're going for here. You can see one way in which we can, why we see these gamma rays. You can see starlight going into an electron and becoming highly energized because of a very energized electron converts it from starlight to gamma rays. This process is called inverse Compton scattering, as I will mention in detail. So, once again, this is the electromagnetic spectrum. It goes from tiny waves to longer waves. And I want to say, gamma ray astronomy is really the true and proper continuation of astronomy above all other attempts. The whole point is to observe the sky in as many wavelengths as possible, in as much detail as possible, then to phenomenologically discover theories. The funding decisions concerning astronomy, I would say, is questionable in America at the moment, especially considering the initiatives of foreign countries, like all of the foreign countries that have investment in astronomy, they invested quite a lot of money and time in gamma ray astronomy, where we have not given it much attention for some reason and seem to keep trying to fund things that don't work. So gamma ray astronomy. I I was quite amazed by my adventure in gamma ray astronomy. I truly see it as an epic field. So to have some context in the background, there's a scientist who spent pretty much his whole work life trying to detect any significant sources in the gamma ray region. It was like he completely isolated himself from the world, pretty much trying to find something that can't be signed for his whole life. Some people would question why study such a thing. Why spend so much time on a thing that doesn't really help mankind or humankind? I believe that the foundations that lead to our ability for such pure revelations to observe the secrets of the universe can help us far more than the persistent struggle of following unreasonable routines. Venturing through the clearer darkness that is American politics to have reason to be heard for a better future is a challenge that really requires not only genius, but to be able to stare evil in the face and laugh at it with a clenching fist. I would say there are probably quite a lot of smart people that have many solutions to many of our problems, but they have to venture through a lot of political dangers, and it's no longer a question that there are political dangers. Politicians come out and blatantly say that their lives are in danger, well, as they speak. I feel that has been, and that it is even questionable. You don't even know what to trust, let alone statements like that. But a field that has been battling with borderline such significant measurements for years has finally seen the light. So let's go in a little bit of history. This used to be a postdoc at Iowa State. He's you used to work with my advisor. He suddenly disappeared. My father didn't talk about much of it. He recently got a job. Um, so he highlights a good introduction. Cosmic rays are the highest energy particles known to mankind, with energies recorded up to 10 to the 20 electron volts. Roughly, this is a joke, the energy of Andy Murray's second syrup. Since their discovery in 1912 by Victor Hess, the origins of these cosmic rays has remained a mystery, and they're still kind of mysterious. We still don't have definitive results, but we have come a lot closer. Through significant work has been done, and many advances have been made. The origin of these particles and how they accelerate to such extraordinary energies remain one of the key questions in astrophysics, and is still the subject of detailed research over 100 years of study. Cosmic rays propagation can be explained with the following equations. So you can see this is this change of cosmic ray density per time as a function of these three parameters: position, momentum, and t, where it being a function of position, or sorry, it being a function of momentum is supposed to represent it in momentum space. But there are a lot of actually variations of this. If you look up cosmic ray propagation equation, they're all slightly different. There is one main component to it, the diffusion equation, which is a more generalized equation that goes beyond cosmic rays. You can see fixed laws of diffusion. It's generally related to diffusion. It has the same format over here. You need a diffusion coefficient d, which isn't necessarily constant, is the main idea here, and the gradient of your density. In this case, we're studying cosmic ray densities, and cosmic rays, in the common term, are charged particles accelerating at rapid speeds. Cosmic rays are the highest energy particles known to mankind, as Ralph was saying. So you can see this equation over here. It's illustrated for a specific environment. You always have your diffusion term over there and your local charge as a source. He has some other parameters which you can see in some of these searches over here. This one has a convective galactic wind and an annihilation rate. You don't always see the annihilation rate, but I believe he is expressing it for galactic wind, so we should see that term also. Might be in a slightly different format. I don't know if he even specifies which one it is for specifically, because you can have cosmic rays in different environments, as we'll say, because we suspect different sources. These equations don't match fully, as I haven't seen a lot of annihilation rates, to be honest. But you get the idea. A good term to add is energy loss, other than diffusion and injection. It loses energy as it collides with things outside of its system. So in this cosmic ray diffusion equation, which is describing the cosmic ray density per unit of total particle momentum P at position R, Q is the source, as we said. D is the spatial diffusion coefficient we were talking about. It doesn't have to be constant everywhere. You can see it has two terms, two indices. V is the convection velocity. So over here, we are considering convection. Right? One of these have convection for sure, but convective galactic queen. That's why I thought they were the same, but it's still written slightly different. So over here, you see it's a partition function number density. And you have obviously the momentum gain or loss, and this other D is the momentum diffusion coefficient for diffusive reacceleration. Then you have your time scales for loss by fragmentation or decay, which is always the case in radiation. So the collaboration I joined that I was talking about is called Veritas. It's I think it's the only gamma ray astronomy collaboration in America. It's still not doing as well as the ones in Europe, but it is truly formed of very skilled and highly passionate individuals. It was quite a pleasure to be a part of the collaboration. They have a hierarchy of so many resources. I learned quite a lot. In this field, you literally apply every part of physics in it, or almost every part of physics. One very nice link that I like to go to is dissertations. So I'll get that elsewhere. But they have every thesis ever published within the collaboration. Um, if you read all of these, you would know everything you need to know about gamma ray astronomy, to be honest. Even more than that. A lot of these theses are very well written and explain a lot of advanced terms very well. One that is particularly good at explanation, actually, the overwhelming detail that goes throughout this whole process is this thesis by Rita Wells, particularly her language that she uses above anything. Okay, now, so this is the person that spent most of his work life trying to find significant gamma ray results. And what I find interesting about this person, if you look up his name, you don't really find much. It's kind of like he was a ghost. He was trying to see the unseen for most of his life. Probably didn't have a really easy time at doing it either. Going home every night saying, "Well, it's been 20 years, so I haven't seen anything." But you can see this review on Tuscan.com about him. This is the only source of information I found about him personally, actually. Pioneered the science of gamma ray astronomy and led development of Veritas array on the slopes of Mount Hopkins. Visionary scientist who opened a new window on the universe. The director of the Harvard Smithsonian Center. He struggled a lot to get it over here. These are two parts of his book, which I will show you in a second. But there are several peculiarities that uniquely pertain to astronomy in the gamma ray regime. These factors make gamma ray astronomy particularly difficult and have resulted in the relative slow development of the discipline. The first demonstration of the existence of cosmic gamma rays came from observation made by the Gamma Ray Telescope Explorer 11 in 1965. This telescope, with a small collection area and full angular resolution, established that there was a flux of gamma rays above the Earth's atmosphere, but not where they came from. The result was sufficient to spur further efforts aimed at the improvements of the detection techniques. Going over here, as might be expected in a new field with binary detectors, weak sources and strong competition between experimental groups, there were many conflicting claims on source detection, but all had weak statistics. With hindsight, the detection of the Crab pulsar was the first credible detection and served to motivate the field to develop new techniques. And that didn't happen after quite a while. This is his very own presentation. Oh, awesome. Right over here. This is his very own presentation. This 1967 was when the telescope was first built at Harvard, the single telescope, but not Veritas, so that we're talking about an array of telescopes. That introduces you to gamma ray astronomy. He starts out with the electromagnetic spectrum, like we said. Gamma ray astronomers have two big problems. No optics detector area equals collision area. The atmosphere equal 1 meter thickness of lead. They need a collection area and they need to work with the atmosphere. Solutions to the problem of atmosphere is that when gamma ray goes into the atmosphere, well, over here it shows you Mount Everest, I guess, which is nice. And you build it beyond the atmosphere, I guess. Earth's atmosphere, enemy of astronomy. So this is true for most cases. It's not true for gamma ray astronomy, as we will say over here. There are a lot of limitations through the atmosphere that block gamma ray radiation, and we saw this actually in the very first few slides. But it's not a problem for gamma ray astronomy. Why is that? Well, this is a space-based telescope. So when a gamma ray hits the atmosphere, or when it hits a specific crystal that's in the Compton Ray Gamma Ray Observatory, is part of a telescope that was released, or when the other telescope that was released, it's a gamma ray that's at a very high energy going through a medium. It interacts with a magnetic field, causing it to produce positron electron pairs. And those are charged particles that are super fast going to a medium that isn't vacuum, and it produces an effect called Cherenkov radiation. Those particles emit radiation because they're going so fast. You can see this over here. And then that radiation once again converts to positron electron pairs, and the cycle keeps happening again, and you get this whole beam of light. And you can study the Cherenkov waves in multiple ways. You can split them into different parts and study the speeds at different parts. So the Earth's atmosphere is our friend after all. It not only is our friend, it makes it possible to observe very high energy radiation because we see the Cherenkov radiation instead of the gamma ray radiation. By the time the Cherenkov radiation actually hits the ground, after it's already converted to secondary lights of secondary showers, it slows down to the UV range where it can be detected by photomultiplier tubes that detect UV spectra. And you can see you have different parts of the showers. First interaction typically at elevation of 20 kilometers. Electromagnetic cascade starting with electron positron pair, opening angle, Cherenkov light from relativistic electrons. So 3 parts. Above 10 kilometers, you have 20% of light generated in a specific direction at that angle, Cherenkov angle, like I was showing you. So afterwards, the intermediate, you have shower maximum, cylinder length of 4 kilometers, and 50% of the light. And below 6 kilometers, you have local particles, 25%, confusing with large fluctuations. Detector level, disk of light with diameter 120 meters and 2 to 3 nanoseconds, with 1 meter thick. From 100 giga-electron volts primary, typical photon density in blue light is about 5 photons per meter squared. Out to 120 meters from axis, detectable with a collector of aperture a few meters squared. But the main part of it creates 3 separate parts, and they don't all arrive together. They arrive at, well, actually, they're not all grouped together, but they travel at different speeds. I think different parts of the showers do catch up to each other, but I'm not sure about that. Cherenkov light shower from a hadron-initiated cascade. So we were talking about if it was a gamma ray coming, but what about a primary cosmic ray? You have both, right? You have cosmic rays everywhere. You get different shapes of waves, and you can try to separate those different shapes and try to figure out which are the gamma rays, which are the protons that also leave cascades of showers through different mechanisms. Starting with pion production, as you see over here. I'll elaborate more a little bit. The Cherenkov light shower from an electron-initiated cascade. Cosmic electrons are actually quite few, less than 1% of hadronic background, so it's quite difficult to find them out. It's like not quite like finding Waldo, but it is tough. You can describe the integration time of the multiplier pulse counting system like that. And then finally, the light signal you can define as such and integrate between 2 wavelengths. And you have the response curve of the photomultiplier tube, which responds to different wavelengths at different quantum efficiencies. This is the Cherenkov photon flux. This is your signal to noise, essentially. So far we've covered quite a lot of information. I don't have time to pause because there's so much information to cover. This is the efficiency of the photomultiplier tubes per different wavelengths. But it is also different for what it's receiving. For Cherenkov light, you have A over here. It peaks at a lower wavelength like that. But other types of light, they peak at different wavelengths, like you can see. On sky background light, for example. So these are some useful numbers he talks about, but not really too important at the moment. So he also talks a bit of detail about things that will be better elaborated in the future slides. But it took him quite a long time to find, from 1967 to 2007, first telescope as opposed to Veritas. And it took him quite a lot of time to find observation, like it says. Continuing on. So this is a good paper that highlights the summary. I'm going to go through it real quick. So 1980s. This is after 1967, where the Whipple telescope was built. She's talking about her experience in ordering specific parts that are useful for building a telescope. For multiplier tubes, as it says, great deal of NIM electronics, 4 telescopes in the array. And yeah, the different telescopes, like I was saying. Starting point is a paper published by Weeks. They describe some simulations that they had performed of Cherenkov light from gamma ray and proton-initiated showers. It is a big point about this, actually. How we reconstruct the cascade showers we received on the ground through simulations to the initial proton entry through the atmosphere. We use simulations to reverse engineer what we think the gamma ray came from, where we think it came from. And he highlights this more in his book. The first part is actually available on Amazon, and it has a free sample within it. But going on to the end, so the full 35 years, you have a group of array of Cherenkov telescopes, Hess, Magic, and Veritas, all in different parts of the world, and they're all working to observe very high, very high energy astrophysics in the gamma ray region. So this is another quote from Weeks. This is a professor who was part of my collaboration who has quite a nice illustration of what happens when a gamma ray hits our atmosphere. You get these secondary showers. You can see the positron electron pair, and then you see a gamma ray and the electron going about its business, and another gamma ray because it's going faster than or very close to the speed of, well, faster than the speed of light in a vacuum, in non-vacuum. So this the relative speed of light is slower in different mediums, so it is an opportunity for charges to go faster than it if you're in the medium, like the atmosphere. And she has some pretty good slides I'll show later. So telescope with photomultiplier tubes that read UV light. Fast, blue sensitive broadband light detectors are available in the form of multiplier tubes. The peak quantum efficiency is typically 15%, and the response curve you can see in this graph over here. We already talked about that. And because of how the whole telescope is built, it's far better to use these multiplier tubes than the CDD detectors, which would be highly expensive for such a wide area, even for an individual telescope. This is quite a nice description of the general research that's done for high energy astrophysics and for Veritas by the previous professor's old mentor. Particles more energetic than any man-made accelerator can produce are continuously bombarding the Earth. We do not understand where these high-energy cosmic rays come from or how they are accelerated to such tremendous energies in astrophysical systems. The vast majority are charged particles which are deflected in the galactic magnetic fields, such that their arrival direction tells little about whence they came. Gamma rays, while much rarer, arrive at Earth unperturbed, while still appearing to come from their true source. By finding and studying sources of high gamma rays, we can identify objects where particle acceleration is taking place and learn the mechanisms involved. One important class of gamma rays is blazars. I think his research was more involved in blazars, which is why he gives it more importance, but there are also other sources. But blazars are a very important source. They're active galactic uh, nuclei, galaxies with an active galactic nuclei. So not all black holes have an accretion disk and are shooting a very bright light out. Those are activated black holes, or in this case, supermassive black holes. And they accelerate a lot of particles at very high speeds. And another thing he talks about, which is quite interesting actually, is gamma ray bursts. While we're still not sure what they always are, I believe there might also be different gamma ray bursts, but we get this bursts of gamma rays from different unpredictable location, making them challenging to study. I believe one of the groups that are trying to understand them are in charge of looking for extraterrestrial life, but it more or less uses Fourier transforms to decode the signal that we are receiving. That's at least one method to do, though. Another interesting one is low energy photons from the cosmic ray microwave background can collide with high energy gamma rays, or starlight, like I said, to produce an electron positron pair, effectively absorbing some of the gamma rays. Okay, let's keep going. So we talked some bit about a telescope. You have an array of telescope photomultiplier tubes. How do we detect them? How do we analyze the data, that is? So first of all, what classifies a trigger when you get a bunch of light? So there are three phases that the telescope has to go through. The first trigger uses a constant fraction discriminator embedded in each pixel to determine output pulse if a voltage bias is reached. So you have to reach a certain voltage from the energy you get in a pixel in the telescope to elaborate a trigger. Then there's a second step in which you use the location of different pixels and the timing to activate a second trigger. Then there's a third one where it's actually between different telescopes. And then you have an actual something that's readable. And you need to do this because you have a bunch of random light coming in out all the time, but you want like light that actually leaves a pattern, like you show over here. This is part of a shower, and you can put them all together to reconstruct the shower fully, and then do the reverse engineering thing I was talking about. And there's quite a lot of intensive hardware that is created not only to build a telescope, but to process the signaling of the telescope. This Professor Holder, he's quite smart, I would say, with his electronics. So keep in mind that this was a paper. This was quite a while ago, 2005, but it uses very advanced digitized techniques to process the information from the telescope. So I told you what initiates a trigger. I didn't tell you the software you use or the mechanical devices you use. So you have your photomultiplier tubes. Reflecting light cones have now been installed in camera face, increase overall photon collection efficiency by 30. After you get the signals and you go through the triggers, each PMT signal is digitized by a custom-built 8-bit flash ADC system sampling at 500 MHz with a memory depth of 32 microseconds. The FADC readout window and size are programmable. Figure 3 shows a typical FAD trace over here. Readout window and size. Oh yeah, figure 3 shows a typical trace with a readout window of 48 nanoseconds. These flashes happen really fast is another thing that you should keep in mind. The use of FADC as opposed to simple charge integrating ADCs allows us to investigate various digital signal processing techniques to improve the signal noise ratio in each channel, as well as providing information about the time structure of a Cherenkov image in the camera. Another thing that is not that I would like to highlight is there's not only one reader, but there's a second one. If there's this pulse can actually overwhelm or oversaturate this flash ADC system. There's a secondary system that's made to do that, and it only takes it lowers the gain of the receiving signal, so you need to multiply it later. That having two separate gains going into your system is actually quite a complicated procedure because you need to create a proper continuity between the two gains, between where one ends and one leaves off, for you to accurately interpret the data or have any data that gives you significant meanings. So That's the telescope itself. Now you go on to analysis tools. This is one of the analysis tools used. This is just a virtual part of it. But the whole analysis goes through multiple steps. First of all, you have to calibrate the data to before you actually start seeing sources. When you extract the signal, after you do the image analysis, there are 5 steps that you pretty much go through to get the full reconstruction. You start off by getting the shower parameters, which I'll talk about right after this paper actually. First of all, you have to clean the data. Not all of the pixels are always stable, not all of the data actually is valid. After you clean it, you can then analyze the parameters of the shower. And you also, like I said, you have to distinguish between the energy, the background, and the sources because they have different shower shapes. And there's quite an amount of detail into doing that, actually. You have to, like any astronomical application, you have to remove random data like sky brightness fluctuations. Not random, but you also do have to remove random data. This is another thing, which is what we call noise, more or less. And after the shower is parameterized, and you can actually study the moments. So you take in these random units and you convert them to real units. You only have digital physical units. You convert those to actual units you can study on a plot. So afterwards, you can study the parameters of a shower and distinguish between the two showers, whether it's a gamma ray or a different type of shower. And like it says, the shower is calculated from the mean intersection points between all possible pairs of telescope images, which we were seeing. And then there are image pairs are weighted by image size, elongation, the relative angle to each other, and their specific image parameters. And there are different ways to proceed at these parts, actually. But even before you do distinguish between different showers, you have to go through the reverse engineering process I was talking about, in which you actually get a location of where you think the gamma ray is actually coming from the sky. And that is the science analysis. And then you can construct a flux of gamma rays once you reconstruct them or reverse engineer them. So going back to this slide, which has quite a lot, these are the parameters you can see in a shower, or at least in a 2D shower. There have also been advanced methods to go beyond this 2D shower input. So I kind of showed you in the last paper where you have parts of the shower in different telescopes and you reconstruct the shower before you construct the gamma ray. By the way, Gavin, has my voice been clear this whole time?
Yes.
Okay, so this is I'll go briefly over this. So it starts out by saying Hillis parameters was usually the only thing used, but today the experiments are equipped with fine-grained cameras and more information. And specifically, they're talking about one of 2 analysis methods is 3D modeling of the Cherenkov light emitted. They add an extra degree of information. And there's a grad student who actually created quite complicated machinery to analyze the 3D modeling through the telescope data. So complicated that my advisor really couldn't figure out how to use it after he left. In the second method, shower images are fitted onto a semi-analytical model which provides a likelihood parameter discriminating gamma rays from hydrons as well as determining the direction of primary gamma rays. So in the paper I was just reading, you might have seen a little bit of boosted decision trees put in there. That is another advancement through this. We're using not only machine learning algorithms, but you can use deep learning algorithms. This is an example of one of the things that you can do. So this is meant for not the beginning stages, or actually, yeah, it loads data that is already processed through the Veritas telescope, in which it has inherent coordinates that you can interpret like through any data visualization tool or data analysis tool. After you get that, it can try to discriminate between, as it says over here, it discriminates between the actual data and the background using TensorFlow, which is just using neural networks. So you have to provide it some data to work with to train on beforehand. So at that point, some very useful data visualization tools, something called Gamma Pi, which is kind of like the big center hub for data visualization. And so I said that you need 5 steps to get to a final product. You start out with the raw images, then you get calibrated images, and then you get reconstructed events, and then you get the gamma-like events. And then after that, even at stage 3, you have to reduce the data set quite a lot because you have quite a lot of information that you need to go through. And then you can actually model it to do actual science. Gamma pi is in this region over here. So you take the gamma ray events and you start doing visualizations. You visualize the gamma rays on sky maps. And why this is nice, I'll show you an example. So you're talking about advanced techniques of observing um, eh, advanced techniques beyond the 2D images of the shower that I was talking about. So you can prescribe a function that this analytic function like I was saying. But an example that's illustrated quite well is another graduate student. Well, the same graduate student that made the very complicated 3D modeling I was talking about. If you look at his enormous thesis, which is right over here, I'll show you an example of the function. Which they do lie over here a little bit. Well, they show you a tutorial and a presentation on what the application does and how to use it and what they use. Actually, they use quite a lot of different packages. Now to install it. Going back to this is probably loaded. In order to produce a gamma ray source spatial model, you'd need a function like this, which each part describes different part leading to the spatial model, whether that's a probability or the area that the wave lands on. Um, Point spread function is actually what I was trying to find. These include the point spread function, PSFP, and energy resolution. So there's a lot of detailing going to this. I just want to highlight the point spread function over here. In order to find the best model of Veritas gamma ray point spread function, several functions were used in an attempt to accurately fit the spatial distribution of events. A Gaussian function, hyperbolic, and a King function were tried, and a King function was decided to work best. So pretty much describing the shape of the gamma ray spread through this function, the morphology of it, which is quite a hard thing to fully digest, but it will make a little bit more sense as we go on. So we talked a lot about processing the data. We didn't talk about specific techniques of how to separate the source from the background other than machine learning or neural networks. This is pretty much like basic data analysis, or like not like more like core data analysis skills. So you can see a source over here, and you can see background around it. A common technique used is to take counts from the on region over here that is highlighting the source, then subtract all these off regions. And it requires a lot more geometry than you would think, especially since you're doing it on a three-dimensional surface. There are different ways to go about this. I'll show you an example through my own data analysis engineering. So this is once again a highlight of what I'm trying to do. I have an inner radius and outer radius and the source region over here. I only want what's within here as an on count. And I want to subtract all these off regions. I don't want to collect anything from over here. And by the way, it's a bit difficult to calculate this area. I did show an example of how to calculate during the simulation presentation using Monte Carlo simulations, but usually the desired method to calculate is a trapezoid summation. So this is a plot of just a portion of a celestial sphere with the source region and the background subtractions, except over here it's actually not calculated correctly. It's in 2D space. To do it in 3D space, what I did is I used this rotation formula in which you rotate around a certain axis. So K would be where your source is, and you want to rotate around that. So I did have to convert from spherical to Cartesian coordinates to do this actually. And then this is the difference between where the actual rings are and where the 2D rings are. And it might not seem that big of a deal over here, but this is a very small region actually of the 3D space. It even looks flat, but it's not flat. But even if it looks flat, you still see some variation of the two difference. So we've seen quite a lot of bit of observation, and we've discovered quite a lot of things. But this leaves like quite a very nice opportunities for theorists to delve in which you can actually prove your results. Gavin, did you have any questions about this so far?
No, I don't think so yet.
Okay. Hopefully I didn't lose you with the 3D modeling. But so going in the behind the theory a little bit. So we're generally more or less, when you're talking about high energy astrophysics, or just you're talking about radiative transfer theories, we're only talking about very high energy, so we only care about some processes, not all these processes. But you don't even have to be a non-relativistic for some of these processes. And it doesn't have to be in astrophysics, but these are some examples in which you transfer energy, or radiative energy specifically. You can have particles that are bound with a system and that are still bound afterwards. An example would be like an electron changing orbital levels within an atom. Or you can have it be freed, so it's ionized. Or you can have it come back, so it's recombined, free to bound. These are different processes. You can also explain some, if not all of these processes using quantum field theory, actually, which I find interesting. And so when you talk about Compton scattering, it's an elastic scattering. It's when collisions between photons and free charges. And if you have a very energetic photon that hits an electron, it will give the electron a lot of energy. Inverse Compton energy is the opposite of that, and it's how we detect those gamma rays, as I was illustrating. That is the main procedure we suspect that releases a lot of high energy gamma rays that we are seeing. And Compton scattering, like I was saying, is just like Thompson scattering. Thompson. But I don't have time to get into detail of these different processes. But then another common radiation that we see is synchrotron radiation, which you can attempt to explain it as just relativistic cyclotron radiation, which you might recognize this as a mass orbiting a larger mass. This is um, the centripetal force, but over here the force is equal to the force caused by the Lorentz force, or by the magnetic field. So you don't have an electric field in this case. This is what the Lorentz force is: electromagnetic acceleration, or force on a charged particle. You only have V and B. Okay, so a very important part of understanding high energy astrophysics is the difference between thermal and non-thermal radiation. And the general concept of having perturbations in your system so that you could lose energy from your system to outside. And the pair of processes that provide photon creation, thermal kinetic energy, is transformed into photons via collision. The photons created in this way are thermal. If the frequency of collisions is sufficiently large, coupling is achieved between the radiation field and particle velocities. So many quanta of radiation are created and destroyed in collisions that there is equipartition between radiation energy and kinetic energy. Such radiation is then thermal at the bound wavelength, or black body wavelength, in accord and equilibrium with the kinetic temperature at that point. In bound scattering, the new photon is provided by a similar photon that originated elsewhere. With much scattering or photon conversion, the coupling between radiation and local kinetic temperature can be lost. Depending on the origin of photons, the entire radiation field can be non-thermal. A radiation field that is in equilibrium with the Maxwellian distribution of particle velocities at the place where it is generated follows the Planck function corresponding to the temperature at that spot. I'll show you a quick graph of what the Planck function is. So this is observing different light intensities for different wavelengths, and it follows the thermal radiation that we were talking about. So taking a quick step back before we go a little bit further than what I said. These are the different types of sources that you get cosmic rays from. We already mentioned active galactic nuclei, which are supermassive black holes. You can also get them from clusters of massive stars, clusters of galaxies, some types of galaxies. Pulsar wind nebula. A pulsar is a rotating neutron star, and the neutron star's wind causes a bow shock with its ambient environment, which is usually the supernova remnant. So neutrons come from the explosion of stars, and you usually have a lot of the remaining parts of the star that exploded outward still floating out there. But you have this rapidly rotating tiny thing in it that's rotating at an intensive speed. So you create a plasma of colliding particles with the ambient medium that is a supernova, and you can charge the particles through there. And supernovae itself, they create a shock to the particles. And binary systems like two black holes or two neutron stars, especially if they're going closer and closer with each other. So here are some examples of non-thermal radiation illustrated by Amy Furness's charts. As we were talking about, you have your synchrotron over here, and the part of self Compton. So self interacting with each other. You have your spectral energy distribution. How much flux you get for different frequencies or wavelengths. And because of this self Compton feature over here, you get a double peak. In the origin of non-thermal radiation. So other than synchrotron, you also have external Compton, external field of photons to additional parameters. It's pretty much what we were talking about over here. Energy, an electron and a photon exchanging energy. But beyond those two, you also have this leptohydronic paradigm. You have so many interactions that you can have between different particles, and a lot of them can have the same common thing over here, gamma rays. And I believe these are intermediate steps between these other processes. As you see, I mean, they don't have to be, but they can be. Fine. Oh, actually, no, that is not correct. Never mind. But having the general environment, you can also observe neutrinos coming out, which is quite a nice probe to make sure that you haven't made this all up and that there are other particles that fit the story. So this is also an example of the constructed energy, the flux density per energy. You can see, this is the data points for the final solution after we went through that whole process. And these are for different telescopes though, or different tools that you put together. You can see IC over here is inverse Compton, SIYN is synchrotron. So if you put together both parts, they fit the data quite well as a single model. And over here you can see the same thing, but they use different models. They don't have quite as much data, but they also use something called multi-zone model. So we talked a lot about, or we talked just very briefly about the particle accelerating in a pulsar wind nebula. This is a pulsar wind nebula, by the way. It's not specific. We're not examining anything else. Specifically, a pulsar, one of the sources of cosmic rays. You're treating it. It's not. There's not just one reason acceleration, but there are 20 zones of expanding shells, initially spherically symmetrical. Evolution in time until the system age assumed its pulsar characteristic is reached. Burst-like injection. They're just adding a little bit of creativity to that. Wasn't always the case. So you can see over here, you might know what type of equation this is. This is two broken power law equations. And we derive this from experimentation. The question is, can we use that, or can we derive this theoretically? We actually, this is a phenomenological sequence in which we're deriving this after we see it, and there are derivations to it. So first of all, I have to give you just a little bit of information about thermal statistics. So thermal statistics is treating a system as you're observing the microstates of a system and analyzing them separately. It is also a tool very useful to apply to quantum statistics, since it's usually tiny little parts that make bigger parts. So how this is your the different small microstates. In this case, they're just particles, and this is you're describing their average number density over here, or the expected number of particles in an energy state I, given a certain amount of energy. So if there's a certain amount of temperature, well, both their energy density, and their temperature. And well, it should explain what mu is over here, but it's specific to the microparticle that you're studying. It's the chemical potential. And yeah, this is the energy. T is the absolute temperature. And G is also specific to degeneracy, which is specific to your system. But let me go to the derivation real quick. So you can imagine observing multiple different microparts and taking a summation to describe them all. It starts with a grand partition function. A quantum system of non-interacting boson is naturally derived from the grand canonical ensemble without any approximations. Um, Pat, um, are you familiar with this at all, actually?
Yep. I derived it in a class a number of years ago.
Okay, so the point of this, as you describe the whole system as a summation of different parts, and if you take that to infinity, like you do over here, and you apply this simple mathematical trick of applying the exponential out, you get this closed form over here. This is a geometric series that we've seen before. And the average number particle, when you take the average over here, is given as such. So going back to that, now that we know how to describe the energy of the equation, even though I did not give enough detail, or the average particle number, we can look at a derivation for what alpha should be, or how we even get this form to begin with. So this is generally, you can see the flux of your number density per area, per steradian, per energy. It gives you this specific power law relationship as we were seeing the spectral energy distribution. But why? Why do we only seen this experimentally? How can we prove that? So we're dealing with relativistic particles. More or less they have the energy density of a photon, virtually massless. And you equate them to energy states that are proportional to the square of their energy. So if you take the mean average per particle, you apply this average equation, and we already know what f is. You get these analytic functions, gamma and zeta, as a solution. Since they're analytic functions, we can find exact solutions to them. And one more definition that you need is the heat capacity per evaporated boson, which is specific to thermal statistics, but you can solve for what alpha is. You still don't know at this point that it follows the general form, but you can solve for alpha over here. There's also this entropy equation that's also fundamental to thermal mechanics. You can get, if you combine two equations, this equation and equation number 5 over here, that's where you get the energy component. And you put a exponential and a logarithm set. They're both just logarithms, so you can take the logarithm out. But you get this distribution in general. And we already know what alpha is, like I was showing you. And it matches pretty well with the experimental results of alpha. One important note that I wanted to highlight out over here. So this is a similar paper. The one important note is a more detailed interacting quantum field theoretical calculation of alpha power laws exponents involves the construction of single particle spectral functions in the context of thermal quantum field theory. I find that quite interesting. That is actually beyond my ability, but I find it just interesting that you can solve it to that level of detail. So this is another interesting paper in which They solve for a probability density function of particles. We elaborate a statistical theory to deal with this problem, relating the composite probability to obtain a flux at the Earth and the single source probability P to contribute with a flux. The problem being is they want everything to be like derived from pure theory. I like have no loopholes, I guess. I mean, you can read it over here. But the main difficulty arises from the fact that P is a heavy tail distribution characterized by power law, broken power law behavior up to very large fluxes. As we saw, the power law was broken into two parts. But keep going. So I'll just highlight the main important part. So they generally start off with the main cosmic ray flux in obeying the fusion equation we were talking about. But something that how they deal with this is, which I find appealing, is they describe the different flux equations. They quantize it or treat it as discrete values, and which you can also treat as discrete values depending on the point charges instead, as they do over here. This is just them expressing the total charge in terms of different discrete charges. This is the flux in terms of different charges in this function. But I don't have more time to go into more detail of it, but I just find it interesting, and they do have good results in the end. So once again, they're finding a probability density function. So not quite the same thing as the last paper, but their approach is aesthetic. But going beyond that, it highlights it over here actually. So this is a very good paper written on high energy astrophysics in general. And I'm gonna go over here to the stress energy tensor. So if you remember last week we were talking about Einstein's equation. We only very briefly mentioned the stress energy tensor. So we only mentioned this left part over here, the Riemann tensor and the Ricci tensor. But we didn't mention what this part was on the right side. So using this Riemann notation, you can set it equal to a source, which is exactly what this is. And it goes back to what a stress energy momentum tensor is. It's relating an energy density to a momentum density, or to a pressure, or more or less density and flux of energy and momentum. And this is perfect for electromagnetism. And this is how you would truly write Maxwell's equations in its full dimensions. But going back to this paper, so they also try to derive, or succeed to derive, the equations from scratch. They start out with this tensor energy equation. Electromagnetic field is a solution of Maxwell equation. And they talk about the four coordinates and the flux density, expressing the electromagnetic field tensor through the four potential, and rewrite Maxwell equations for the potential and the Lorentz gauge in the form of a inhomogeneous wave equation. And they treat the charge, creates the forecurrent. So they also discretize this different points. And you can see their functions of space and time. And you can solve for these equations and solve for the electromagnetic field, the E field, and the B field. This is quite long. So they typically make approximations to this. But this is just when you have like you're applying this in 4-dimension and you have a source creating a charge density source is creating electromagnetic fields. And so you're studying, the whole point of this is studying acceleration in electromagnetic fields in the proper amount of dimensions. So they say they make approximations and based on like certain conditions. And this is the energy flux. This is a known equation which you can derive from the units, but the Poynting vector. So this is also quite detailed, more than we have the time to truly appreciate. But the point is that they have a final expression for, well, they will have a final expression for the power generated. So the Lamore formula is actually the most general way to describe particle radiation. You usually apply different conditions to it to simplify it even more based on the situation. It's the most general form. Describes particle radiation. And they also talk about curvature radiation, which we were talking about, but the point is that they do this using high-level math rather than the Euclidean three-dimensional geometry that we usually use. You don't need to apply it in that much detail to agree with the observations that we see, but so this is a good point to talk about a different part of high energy astrophysics. We've only talked about the gamma ray region, but there's a whole different part, it's the X-ray region. There's a lot that happens between the two. There's a lot of that's common between the two. So this is Integral is a telescope released by a European agency. Like in the last 25 years, has been collecting new generation. Well, no, it's been collecting X-ray data. The closest equivalent to it would be Chandra in America, but I believe they cover slightly different energy regions. Forget which one dominates the other. But another thing I like about this paper, they provide very good background to general high energy phenomena, and they're mainly just talking about X-rays. They're talking about a pulsar, specific studying of a pulsar. So a pulsar does emit a lot of X-rays. They say they observed some radiation at X-rays and soft gamma rays. Pulse emission powered by the rotation of the strong electromagnetic field anchored to the NS surface or dissipation. Neutron star surface. Over here, they're talking about accreting millisecond parsecs, which is more or less the background that I was entailing. So, a final specific point. If you look over here, these are X-ray emission mechanisms, and you can see a lot of them are quite similar to gamma ray emission mechanisms. So wherever you see gamma rays, it's likely that you'll also see X-rays. Also, two fields that you have to put hand in hand. Brimstone radiation, by the way, is just free to free. We did not cover that part, but imagine an electron floating around and then it highly glows over like a proton as it passes by. Well, slightly grazes a proton as it passes by. Gavin, did you have any questions?
Um, I guess one question was how much are the spectroscopic profiles like blurred while um, while they're being transmitted through space? So you have, for instance, the original spectroscopic profile of the star um, right where it exists, but then it takes, however many light years to reach Earth. Is it mostly perfectly preserved, or do you have to adjust for that?
That's I think this is your exact answer. So it's very unlikely for it to interact with. There are two answers to that. It's both very unlikely for it to interact with anything on its trajectory from Earth from its source, and there are enough of it where, as if some of them deviate, the probability is in your favor. That is the case for gamma rays. That is not the case for charged particles at all. Charged particles, they actually follow an isotropic medium throughout the galaxy. But it completely depends on the type of particle you have. In light, if you don't have anything absorbing it or blocking it, then you're fine. You're pretty safe for gamma rays because they're so small.
Okay.
Let me look at optical depths of gamma rays and yeah, this is I know that so I don't remember this in detail, but I remember some specifics concerning active galactic nuclei, which you're studying gamma rays that are very, very far away, like ridiculously far away, and where the statistics start to falter a bit more. But I'm not sure about that. But like not to an extent where you can't do any significant science results.
Okay. Thanks for the answer. Yeah.
Okay, cool. So this will indeed be our last meeting. I don't know how useful it is for you to show you derivations without explaining them very clearly. Um, I don't know, this is for physics people, it's not as much useful. I don't know if it's useful for a little bit more for math people. Um, For me personally, it just depends on how awake I am.
Mm-hmm. I find the derivations interesting.
Yeah, and these lecture slides will also be online, so you're only meant to see a sneak peek at them.
Okay. Well, I guess have a good Thanksgiving. And yeah.